Sir Isaac Newton. He was a scientist, mathematician, and astronomer. He was born on January 4, 1643, in Woolsthorpe, England. His father's name was Isaac Newton Sr., and mother's name was Hannah Ayscough. His father was a farmer and had died 3 months before Newton's birth. His mother remarried when Isaac was 3 years old and left young Isaac in the care of his grandparents. Isaac attended school, where he was an adequate student. At one point, his mother tried to take him out of school so he could help on the farm, but Isaac had no interest in becoming a farmer and was soon back at school. Newton attained his preliminary education from the King's School in Grantham, where he excelled and achieved the top rank. He then enrolled himself as a sizar at the Trinity College, Cambridge, in 1661. The young Isaac Newton is sitting in his garden when an apple falls on his head, and, in a stroke of brilliant insight, he suddenly comes up with his theory of gravity. He would spend much of his life at Cambridge, becoming a professor of mathematics and a fellow of the Royal Society. He eventually was elected to represent Cambridge University as a Member of Parliament. Isaac had to leave Cambridge from 1665 to 1667 because of the Great Plague. He spent these 2 years in study and isolation at his home in Woolsthorpe, developing his theories on calculus, gravity, and the laws of motion. In 1696, Newton became the Warden of the Royal Mint in London. He took his duties seriously and tried to get rid of corruption as well as to reform the currency of England. He was elected President of the Royal Society in 1703 and was knighted by Queen Anne in 1705. In 1687, Newton published his most important work, called the Philosophiae Naturalis Principia Mathematica. In this work, he described the 3 laws of motion, as well as the law of universal gravity. This work would go down as one of the most important works in the history of science. It not only introduced the theory of gravity, but defined the principles of modern physics. Outlined in the Principia, his theory about gravity helped to explain the movements of the planets and the Sun. This theory is known today as Newton's law of universal gravitation. Newton's laws of motion were 3 fundamental laws of physics that laid the foundation for classical mechanics. Newton invented a whole new type of mathematics, which he called fluxions. Today we call this math calculus, and it is an important type of math used in advanced engineering and science. In 1668, Newton invented the reflecting telescope. This type of telescope uses mirrors to reflect light and form an image. Nearly all of the major telescopes used in astronomy today are reflecting telescopes. He died at March 31, 1727, in London, England, at the age of 84. To every action, there is always opposed an equal reaction, said Isaac Newton.
Sir Isaac Newton, 1643 to 1727. An English scientist and mathematician famous for his discovery of the law of gravity. He also discovered the 3 laws of motion. He published them in his book Philosophiae Naturalis Principia Mathematica, or Mathematic Principles of Natural Philosophy, year 1687. Today these laws are known as Newton's laws of motion, and describe the motion of all objects on the scale we experience in our everyday lives. Here is an image of Sir Isaac Newton. One of his famous quote is, "If I have ever made any valuable discoveries, it has been owing more to patient attention than to any other talent."
Imagine you're sitting on a recliner chair watching your favorite movie on a lazy Sunday. And your mom calls out your name and asks you to run some errands. You can imagine how difficult it would be for you to get up and do the work. Imagine you're practicing for your 100 meters race on this track, and somebody asks you to stop immediately within a second. Will you be able to do it? What if you're suddenly asked to turn towards the right? Will you be able to turn immediately? The answer to both the questions would be a no. You can stop, yes, but gradually. You can also turn, but not sharply. And guess what? It's the same story with every object. Every object will continue to do what it's doing. If it's at rest, it will remain at rest. And if it's in motion, it will stay in motion. But what can change this? Yes, only an unbalanced force can change this. If it's at rest and an unbalanced force acts on it, it will move. If it's in constant motion and an unbalanced force acts on it, it may accelerate or change direction. And this is nothing but the Newton's first law of motion. Here's the correct definition. An object at rest stays at rest, and an object in motion stays in motion with the same speed and the same direction, unless acted upon by an unbalanced force. In simple words, it means that the objects continue to do what they're doing unless some external unbalanced force acts on them. We can also understand this using a simple diagram. If the forces are balanced, there can be two cases. An object may be at rest, or an object will be in motion at a non-zero constant velocity in a particular direction. These can be the only two cases when the forces are balanced. In the first case, the object will continue to remain at rest, and in the second, the object will continue to stay in motion at the same velocity and in the same direction. Don't forget, these two cases will remain true only if the forces are balanced. In the next video, we will look at a few applications of the first law of motion. To understand inertia, we need to look at Newton's first law of motion again. Here it is. In simple words, this means that objects tend to keep on doing what they are doing. It is the natural tendency of every object to resist change in their state of motion. If they are at rest, they would prefer staying at rest, and if they are moving at a constant velocity, they would want to continue doing so. This tendency of objects is called nothing but inertia. It's the natural tendency of an object to resist change in its state of motion. Yes, you already knew what inertia is. And yes, Newton's first law of motion is also called the law of inertia. Do you think all objects have the same inertia? All objects resist changes to their state of motion, right? So all should have the same inertia, correct? Well, not really. Because inertia tells us how strong an object's tendency is to resist change in its state of motion. Think of it like this. There's a tiny brick kept on a table next to a relatively larger and a heavier brick. Which one do you think would be easier to push? Without doubt, the tiny brick, correct? Yes, but why is that? It's because the heavier brick's tendency to resist change in motion is more. The heavier the object, the more is its tendency to resist the change in motion. The more mass an object has, greater will be its inertia. So if we apply equal force to both these bricks, the tiny brick will move further as compared to the larger brick. The heavier brick has more inertia. How can we relate inertia and mass? Inertia is the tendency of an object to resist changes to its state of motion, and the mass of an object is the measure of its inertia. In the next part of this video, we will understand this relation with a few interesting examples.
If Newton's first law of motion is called the law of inertia, we must first define inertia. Inertia is the tendency of object to keep doing what they are doing. If an object is resting, it will tend to keep resting. If an object is moving, it will tend to keep moving. This property is called inertia. Why do the dishes stay on the table when the tablecloth is pulled out? The dishes stay because of their inertia, their tendency to keep doing what they are already doing. Mass and inertia. Mass is the amount of matter in an object. The more mass an object has, the more inertia the object has. Bigger or more massive objects are harder to start and stop, because they have more mass and therefore more inertia. A weighty problem. Example. If you spend most Sunday afternoons at rest on the sofa, watching football and consuming large quantities of food, what effect does this practice have upon your inertia? Your inertia will most definitely increase. Your mass will increase because of this practice, and if mass increases, then inertia increases. Newton's first law of motion, also known as the law of inertia. Law of inertia states that an object in motion tends to stay in motion and an object at rest tends to stay at rest, unless the object is acted upon by an outside force. The law also says that when an object is moving, it tends to remain moving along a straight line path unless acted on by an outside force. Law of Inertia Example. One of the most common places people feel the first law is in a fast-moving vehicle, such as a car or a bus, that comes to a stop. An outside force stops the vehicle, but the passengers, who have been moving at a high speed, are not stopped and continue to move at the same speed. Another example. An astronaut in space throws a rock. What will the rock do? It will continue to move in a straight line at a constant speed, until an outside force acts on it. Think of a ball in a cart. When you jerk the cart forward, what does the ball do? The ball will hit the back of the cart. Why? The ball's inertia will keep it at rest while the cart moves under it.
Do you remember the Newton's first law of motion? It says that an object will continue to do what it's doing unless acted upon by an unbalanced force or some net force. Now the important question is, what happens when there is net force acting on an object? That's precisely what the second law of motion will discuss. Do you remember understanding the first law of motion with a simple diagram? If the forces are balanced, the acceleration will be zero. In the first case, the object will continue to remain at rest, and in the second, the object will continue to stay in motion at the same velocity and in the same direction. Don't forget, these two cases will remain true only if the forces are balanced. Only if the net force is zero. Now let's try to create a similar diagram for the second case. If the forces are unbalanced, then there will be acceleration. We saw that in the previous video. And now we come to the interesting part. Let me ask you a question and I'm sure you can answer it. On which two factors do you think the acceleration will depend on? I want you to tax your brain a bit. Let me repeat my question. On which two factors do you think will the acceleration depend on? Okay, let's say there's an object on a table. You apply a net force of 10 units on it. And then you apply a net force of 20 units on it. In which case do you think the acceleration will be more? Of course, the one in which the force was more. So we can say that one of the things the acceleration depends on is net force. If it's more, then more will be the acceleration. If it's less, then lesser will be the acceleration. Acceleration depends directly on the net force. Come on, now I want you to think about the second quantity the acceleration will depend on. Let's say there are two objects on the table. One has a mass of 3 kilograms and the other has a mass of 5 kilograms. Now, if you apply net force of 10 units to each of them, which one do you think will accelerate more? Surely it's the 3 kg one because it has lesser mass. Lesser the mass, more the acceleration. And more the mass, lesser the acceleration. Hence we can say that acceleration depends inversely on the object's mass. If you understand this concept well, then understanding the second law of motion will be very easy. Mathematically, it can be written like this. In simple terms, the acceleration is directly proportional to the net force applied, and and inversely proportion to the mass of the object. That's the second law. Or as more people understand it, like this. The net force is the product of mass and acceleration. With this, can you tell me the units of force? That should be easy. The standard unit of mass is kilograms, and that of acceleration is meters per second squared. So the unit of force is kilograms times meters per second squared. And this is what we call as Newton. 1 Newton is 1 kilogram times meters per second squared. So if the mass of the object is 10 kilograms and the acceleration is 10 meters per second squared, then the force will equal 100 newtons. We can say that 1 Newton is defined as the amount of force required to give a 1 kilogram mass and acceleration of 1 meter per second squared.
Let's accept it. Most of us think that mass and weight are pretty much the same thing. Are they? No, they're not. There's a very simple way to understand the difference. Mass is simply the amount of matter that's present in the object. Now consider two situations. One in which an object is on the Earth, and second in which the same object is on the Moon. Will the mass of the object be different in these cases? To answer this question, we ask ourselves another simple question. Will the amount of matter present in the object be different in these cases? Absolutely not. The matter in the object is not changing at all, which is why the mass will be the same in each of the cases. The mass of an object remains constant no matter where it is placed. The standard metric unit of mass is the kilogram. Another concept we'd learnt about an object's mass was that it is a measure of its inertia. Greater the mass of an object, greater will be its inertia. Inertia is nothing but the tendency of an object to resist change in its state of motion. So now we have an idea about what mass is. But what's weight then? How do we understand the weight of an object? Mass is nothing but the measure of how much matter an object has. Weight is a measure of how strongly gravity pulls on that matter. It's the measurement of the gravitational pull of an object. Let's understand this using a simple example. Say there are two places, place A and place B, and there's an object of mass m. In place A, the pull of gravity is x units, and in place B, the pull of gravity is 2x units. Clearly, the pull of gravity is stronger at place B. Now understand this well. The mass of the object will be m at both the places, but the weight of the object will be greater at place B because the pull of gravity is stronger. As the gravity is twice as bigger, the weight of the object will be twice as much at place B as compared to place A. So the weight of an object is a measurement of gravitational force acting on it. How can we understand weight using a formula? We know the Newton's second law of motion, which says that the force acting on an object is the product of its mass and acceleration. When it's acceleration due to gravity, we can replace A with a lowercase g. This force due to gravity is nothing but the weight of the object. So if we consider the weight of an object to be uppercase W, we can rewrite this equation as W equals m times g. So the weight of an object is the product of its mass and acceleration due to gravity. What will be the SI unit of weight? Can you guess? It'll be the same as that of force, Newton. As the value of g at a particular place is constant, we can also say that the weight of the object is directly proportional to its mass. Here's the main takeaway from this video. The mass of an object remains constant everywhere, whereas its weight depends on the gravitational force at the location.
Newton's second law. If you apply more force to an object, it accelerates at a higher rate. If the same force is applied to an object with greater mass, the object accelerates at a slower rate because mass adds inertia. According to Newton, an object will only accelerate if there is a net or unbalanced force acting upon it. The presence of an unbalanced force will accelerate an object, changing its speed, its direction, or both its speed and direction. Newton's second law of motion pertains to the behavior of objects, for which all existing forces are not balanced. The second law states that the acceleration of an object is dependent upon two variables, the net force acting upon the object, and the mass of the object. The acceleration of an object depends directly upon the net force acting upon the object, and inversely upon the mass of the object. As the force acting upon an object is increased, the acceleration of the object is increased. As the mass of an object is increased, the acceleration of the object is decreased. Newton's second law of motion can be formally stated as follows. The acceleration of an object as produced by a net force is directly proportional to the magnitude of the net force, in the same direction as the net force, and inversely proportional to the mass of the object. In other words, how much an object accelerates depends on the mass of the object, and how much force is applied to it. The equation for this is force is equal to mass times acceleration, or F equals m times a. Unit of force is Newton or capital N. SI unit for mass is kilogram or kg. And SI unit for acceleration is meter per second squared. The unit of force is Newton, N. 1 Newton, N, is equal to 1 kilogram meter per second squared. 1 Newton or 1 N is the force required to produce an acceleration of 1 meter per second on a body mass 1 kilogram. 3 forms of the second law. These tables shows the formulas you can use when solving for the acceleration, net force, and mass of an object. You can use A equals F divided by m, or acceleration equals net force divided by mass to solve for the acceleration. F equals m times a, or force equals mass times acceleration, in solving for the net force of an object, and m equals force divided by acceleration in solving for the mass.
The only question you need to ask yourself while studying the third law is, what happens when two objects interact with each other? What happens when you place an object on the table? The object exerts a force on the table, and the subject exerts an upward force on the object. There are two forces that result from this interaction: a force on the table and a force on the object. The magnitudes of the two forces are the same, but the directions are opposite. These forces are called as action and reaction forces. The force exerted by the object on the table was an action force, and the force exerted by the table on the object is the reaction force. What we saw here is nothing but a display of the Newton's third law of motion. Every action has an equal and opposite reaction. That's how simple the third law is. Every action has an equal and opposite reaction. It means that when two objects interact, there is a force on each object. The magnitude of force on the first object equals the magnitude of force on the second one. And what about the direction? The direction of force on the first object is opposite to the direction of force on the second one. Let's talk about more examples. While a frog is swimming, it pushes the water back, and the water pushes its body forward. Now let me ask you a question. Say a bird is flying upwards. Will the Newton's third law apply here? Sometimes the third law is not so obvious. You'd probably say that the bird is the only object here and there's no second object. But that's not correct. The wings of the bird push the air downwards, and the air pushes the bird upwards. Action and reaction forces make it possible for birds to fly. We take one last example to understand something very interesting about the third law. What happens when a gun is fired? You're right, it exerts a forward force on the bullet, and the bullet exerts an equal and opposite reaction force on the gun. And this exists in recoil of the gun. A perfect example of Newton's third law. But hold on. If the force exerted by the gun on the bullet is the same as the force exerted by the bullet on the gun, then why doesn't the gun recoil with the same acceleration as the bullet? The gun recoils, yes, but it doesn't recoil at the same acceleration as the bullet, right? Same magnitude of forces, but different accelerations. Why do you think this happens? Okay, so if your concept of the second law of motion was clear, you wouldn't really be surprised with this. The second law of motion says that the force is the product of the object's mass and acceleration, or the acceleration of the object is equal to the force over its mass. What does this tell us? Yes, if the mass is more, then the acceleration will be less. In this example, the mass of the gun is much more than that of the bullet. Hence, the acceleration of the rifle is lesser than that of the bullet. If you're in a boat and step out of it onto the land, there are two forces involved. You pushing the boat behind and the boat pushing you forward. And that's why you see the boat go behind when you go forward. Now let's say a sailor jumps off a huge ship. The sailor does apply a force on the ship, and the ship also applies a force on the sailor. But do you think the ship will accelerate as much as the sailor? Not really, and I think you know why.
Real-world examples of Newton's third law of motion that states that for every action there is an equal and opposite reaction. The skateboarder, in order to do the kickflip over the bench, needs to first have his force go downward in order to pop the board upward. The jet moves forward because the force of the engine goes backwards. Look at these ladies paddling. They paddle backwards in order to go forward. This basketball bounces upward because it first goes down and the basketball court gives a force upward which causes it to bounce. Look carefully at this jellyfish. In order to move forward, it moves its body backwards, and the water has an opposite reaction and forces the jellyfish forward. Jumping on a trampoline is the same way. The force is downward, and then you have an equal force upward, which causes you to go up. And finally, look at this balloon. When the balloon hits the earth, it has an opposite force which causes it to change direction and go upward. So there we go, some real-world examples of the third law of motion, which states that for every action, there is an equal and opposite reaction.
Newton's third law of motion. Newton's first two laws of motion explain how the motion of a single object changes. Newton's third law describes something else that happens when one object exerts a force on another object. According to Newton's third law of motion, forces always act in equal but opposite pairs. The forces exerted by two objects on each other are often called an action-reaction force pair. Either force can be considered the action force or the reaction force. Action and reaction force pairs don't cancel because they act on different objects. Newton's third law of motion states that, for every action, there is an equal and opposite reaction. This means that when you push on a wall, the wall pushes back on you, with a force equal in strength to the force you exerted. Properties of action and reaction pair forces. 1. Action and reaction forces always come in pairs. 2. Action and reaction forces are equal in magnitude but opposite in direction. 3. Action and reaction forces act on two different bodies. 4. Action and reaction forces have the same line of action. There are also some of action-reaction force pairs that are evident in nature. When you jump, you push down on the ground. The ground then pushes up on you. It is this upward force that pushes you into the air. Propulsion of a fish through the water. The fins help the fish to push water backward. With each push on the water reacts by pushing the fish forward, which propels the fish through the water. The force on the water, backward, is opposite to the direction of the force on the fish, forward. Hence, for every action, there is a force with the same magnitude, but with a different direction, reaction. It is this action-reaction force pair that explains how fishes swim. Next, consider the flying motion of birds. A bird flies by the use of its wings. The wings of a bird push air downward. In turn, the air reacts by pushing the bird upward. Consider the motion of automobile. An automobile is equipped with wheels that spin backwards. As the wheels spin backward, they push the road backward. In turn, the road reacts by pushing the wheels forward. As we walk, our feet push the ground backward. As a reaction, the ground pushes our feet forward, causing us to move forward. A helicopter pushes the air downward by using a specially designed propeller. As it pushes the air pushes back the helicopters, causing the helicopter to be lifted up. Activity A. Directions. Determine if the following statements are true or false. Write T as the statement is true, and F if the statement is wrong. 1. Inertia is the tendency of an object to resist motion. 2. Newton's first law of motion is also called the law of acceleration. 3. If an object is at rest, inertia will keep it at rest. 4. The inertia of an object is determined by its speed. 5. The speed of an object changes only when it is acted on by an unbalanced force. 6. A stationary object resists movement only because of gravity. 7. The tendency of an object to resist a change in motion depends on its mass. 8. If the net force acting on an object is 0, its inertia is also 0. 9. When you are moving at a high rate of speed, inertia makes it hard to stop. 10. Newton's first law of motion applies only to objects that are already moving. B. Directions. Complete the table below. Be sure to include units in your answer.
C. Directions, listed below are action forces. Identify the reaction force. A. Your bottom pushing on your desk seat. B. A bat hitting a baseball. C. Your finger pressing on your phone screen while texting. D. Head bumps ball. E. Enclosed air particles pushes the wall of the balloon outwards.